All right, so last night I asked you to figure out the molecular shape of HNO. All right, so that's the molecular formula, and we're only so far in this unit we're only dealing with formulas of covalent molecules. So the first thing you want to do, step number one, is going to be to write the electron dot formulas. So hydrogen has 1 dot, nitrogen has 5 dots, and oxygen has 6 dots. Now, the reason that hydrogen has 1 is because it's in the first column of the periodic table, so it only has a 1s electron. It's in the first period too, so it only has a 1s electron. Only 1 primary energy level, only 1 sublevel, only 1 electron. Nitrogen over here is in the second row. So what we care about with electron dots are the electrons that correspond to only these elements in the second period of the periodic table. We don't care about those down in the first primary level. Those are not the valence electrons. The valence electrons are those electrons represented by the placement of these atoms in this period of the periodic table. So these two atoms here represent two S sublevel electrons. In the second primary level, S sublevel 2 electrons. And then over here in the P sublevel region, this section of the periodic table is the P sublevel, except for helium, which actually belongs over here. We have 1, 2, 3 more electrons in the P sublevel. Now, both the S sublevel in this row and the P sublevel represented by the elements in this row are valence level electrons. So that's 1, 2, 3, 4, 5 electrons. And that's where we get those 5 dots. Oxygen has 1 more, so it's 6 dots. You put 1 dot on each of the 4 sides, well, until you run out of dots you need. If you only need 3, you'll stop at 3. But if you need 5, you're going to put an extra one and pair it up. If you need 6, you can put 2 more. Pair them up beyond those first 4. So anyway, we are at the point now where we're ready to do the sharing arrangement. Let me find the pen that I want to use for this. So I can share this electron here. Hydrogen only wants 2 electrons. Since it's right here, and it wants to be like its next highest noble gas, that would be helium. Helium only has 2 electrons. By sharing an electron with nitrogen, that would give helium the 2 electrons it wants. I'm sorry, hydrogen the 2 electrons it wants. Nitrogen wants to have 8 because its next highest noble gas is neon. And so does oxygen also want to be like neon. So both of these are going to want to have 8 electrons, 8 valence electrons like neon. So right now this gives nitrogen 6 electrons, oxygen has 6. If I share 2 electrons between nitrogen and oxygen, now both of them have 8. So that's the sharing range. We started out with the electron dot formulas. That's an electron dot formula for just hydrogen, electron dot formula for just the nitrogen, electron dot formula for just the oxygen, and then we transform that into a sharing arrangement in this fashion. Then the next thing we want to do is to squeeze everything together and get a Lewis dot formula. Okay, I need you to do 2 things. I need you to put your name on the top line of this pass and put it in your personal folder, okay? So when you squeeze them together, you squeeze these 2 electrons between the hydrogen and nitrogen. If we put those atoms side to side, the electrons will squeeze together and become over and under. Between nitrogen and oxygen, however, we have 4 electrons. And the tradition for putting 4 electrons between 2 atoms is a kind of box arrangement. Then you have these 2 electrons here and 2 electrons here that are going to remain there. And so this is the Lewis dot formula. From the Lewis dot formula, we're going to find the electron pair shape. And for that, we need to determine the number of sets of electrons around the central atom or the atom we're interested in. We're interested in the nitrogen here. We're using simple molecules, and there's only 3 atoms here. We're looking at the central molecule, a central atom in the molecule. This is our central atom. A set of electrons is defined as all the electrons shared between 2 atoms. So there are 2 electrons shared between hydrogen and nitrogen. That's the set. There are 4 electrons shared between nitrogen and oxygen. That's a set. So there's a total of 2 sets here. Okay? So if I have nitrogen as a central atom, the arrangement that's going to get 2 things as far apart around that as I possibly can is pretty much a straight line. There's no reason to bend it. That will get it closer than necessary. We want them as far apart as we can get them. So I'm going to put 2 electrons here for these 2. And I'm going to put 4 electrons over here for those 4. And that's the electron pair shape. Now we haven't talked about the name of this, but you could probably come up with a name pretty easily that would be reasonable. But to be technical about it, we call it linear. And that sounds really technical, right? Linear? Okay. Right. So then we want the next stage in the process is to take any shared sets of electrons here and replace those shared sets with the atomic symbol of the atom they are shared with. Well, these 2 electrons are shared with this hydrogen. These 4 electrons are shared with this oxygen. And we're not going to worry about these extra electrons on the oxygen because it's not the central atom. So the next thing we're going to do is we're going to put our nitrogen here. We're going to do this in pencil. Redraw exactly the same drawing. Exactly the same drawing. And replace any shared sets with the symbol. And that means we're going to replace these 2 right here with the symbol for hydrogen. And these 4, the set of 4 here with the oxygen. And that's the molecular shape. Okay? And that's also, we didn't change the geometry from this to this. So this is linear and this is linear. Does that make sense? Okay? So this has a name then. Since this is the electron pair shape, we're going to call this a linear. Now, this wasn't part of your homework. Naming it wasn't required. Okay? I only asked you to determine its shape, correct? Okay? But now that you know the name, in the future I expect you to name it, okay? A linear electron pair shape. Okay? Since we didn't change the geometry is the same, we just changed the symbols on the end. This is also linear, but this is not an electron pair shape. Now that we've gotten rid of all the electrons around that central atom, with this drawing there's no more any electrons, we replaced everything with symbols. This is now the molecular shape. So the molecular shape, you reach the molecular shape once you've eliminated all the electron pairs. If there was an extra set of electrons around there, we'd have to draw one more drawing and then erase the electron pair to get the molecular shape. Does that make sense? You remember that? We've done that a few times. All right. So that was your homework. Okay. I'm not going to check it today. I'm just going to go over it because we kind of need to move on and get to our modeling. So if we were going to do the molecular shape of this, okay, we'd have, do a balloon model of this. We would have hydrogen as a sphere, an old knot. We'd have a hot dog shape for that bond right there. But this bond is not a straight line anymore. It's actually, when we look at the actual type of bonds, it's a double bond. And the double bond means I've got a hot dog shape in the middle, but I've got the pi bond I showed you yesterday goes above and below, like this. Okay? And since there are 2 lone pairs over here, we do show those with balloons. Okay? And so you have a balloon, a round balloon like that, and one going back here behind everything. Okay? And so your nitrogen in this is right here where the knot is, and the oxygen would be right here where the knot is there. Okay? So we don't actually show in the balloon model the nitrogen or the oxygen. So nitrogen is the knot right in there, and oxygen is the knot right in there. Okay? These are the lone pairs. The lone pairs here. Okay? So these lone pairs are hybrid orbitals. Lone pairs are always hybrid orbitals. And hybrid orbitals always, well, it depends on the kind of hybridization. Since I have a pi bond here, this is a pi orbital. It comes from an unhybridized p orbital. Then the hybridization on oxygen is sp2. I've got this hybrid orbital, this one, and the one in the back. So these are hybrid orbitals. In this case, they're sp2 hybrids. Okay, if you're not taking notes, you're not practicing for success. You're practicing for failure. Okay? When you write it down, you are helping to commit all this to memory. Okay? The more you practice, the more you're going to succeed, the more likely you are to succeed. The more you practice properly, the more you're more likely to get it right on the test. Okay? So you should be taking notes on this, because even though you may have this on your homework up to this point anyway, if you don't have this in your notes, then you're just not, you're not really getting where you need to go. All right? So then this, and right here are all sp2 hybrid orbitals. Okay? The lone pairs are hybrid orbitals, and this is also an sp2 hybrid orbital. Okay? Well, let's do it this way. Let's say it's an sp2 hybrid orbital like this. So that right there is an sp2 hybrid orbital. The nitrogen has the same kind of hybridization. We've got a p orbital we didn't hybridize that becomes a pi bond. So both the oxygen and the nitrogen have a p orbital they didn't hybridize that becomes a pi bond. Whatever remains then let's see. Oh, I left off the lone pair on the nitrogen, didn't I? Over here. There's a lone pair right there I didn't put on here. Okay. Which means I actually need a balloon tucked in behind here. I thought something didn't look right. Okay. So all of these are sp2 hybrid orbitals. Got that right there. Got this right here is a hybrid orbital. And right in there is a hybrid orbital, sp2 hybrid orbital. And then you have p orbitals that are not hybridized. And that would be right here and there, and right here and there. That's the p orbital right there, and they form a pi bond. So this is the pi bond, two parts of the same bond, just like the p orbital had two balloons. The pi bond's in the same orbital, but it's made of two balloons. And then your sigma bond is right here. Okay, and you got a sigma bond right here. You got a hydrogen right here, and so forth and so on. So there's a lot there to remember. Okay, as we get the balloon models of these more complex molecules, it's a little bit harder to draw everything because there's so much labeling in there. That's why it's important to do the model so you can kind of see everything. That's the idea anyway. All right, so now let's look at what we're doing today. We were working on yesterday H2CO, and we had two hydrogens. Whoops, two hydrogens here with a single dot. Carbon started out with 4 valence electrons. I showed you a moment ago how to figure out the number of valence electrons. Oxygen, we just said, had 6. Share the electrons, so this gets shared here, this can be shared here, then this one can be shared here, and this one here. Electron dot formula then becomes something like this. Four electrons between the carbon and the oxygen, and that box sort of arrangement. There's the Lewis dot formula. Then the electron pair shape, I'm going to put the 4 dots up here this time. That gives us that 3 sets of electrons as far apart as we can get them, and that's called trigonal planar. Okay? That's a trigonal planar shape. It's on a flat plane, It's not tetrahedral because tetrahedral requires 4 arms. We've only got 3 sets of electrons around this central atom here. So we've got 3 arms here. This is trigonal planar. That's an electron pair shape. And from that, then we replace the electron dots, the sets of electron dots, with the atomic symbol of the atoms they are shared with. In this case, all the sets of electrons around this central atom are shared, so we're going to replace all of them. So then carbon is here. We're going to have oxygen on the double set, so oxygen's got to go up here this time. Hydrogen's over here, and hydrogen's over here. And now this is also, we haven't changed the geometry. This geometry and this geometry look the same. I'm sorry. This geometry and this geometry look the same. So this is still trigonal planar. But now, since we don't have any electron pairs left over anywhere, this is the molecular shape. Okay? But when we do the balloon model, we've got to take into account this double bond. Okay? We're not going to have just 3 long balloons as we did when we were doing the models of only single bonds. Okay? We're doing the tetrahedral arrangements. We had only single bonds. Now we've got a double bond we've got to take care of. And a double bond looks different. A double bond comes from an unhybridized p orbital. So I'm going to draw the carbon here, and remember our p orbitals when we did those? They were double balloons. And the oxygen also has an unhybridized p orbital. I'm going to color code this one blue. Then we're going to hybridize all the other valence level orbitals. Let's see. So carbon, when we initially did the orbital notation for carbon, we had this. There's your 1s electrons. There's your 2s orbital and 2 electrons. And then we had 2p, where we had a total of 2 more electrons. So that was the ground state carbon orbital notation. Okay? 1s1, 1s2, there they are. 2s2, 2s1, 2s2, right there. There they are. 2p and 2p for those 2 electrons. Remember, once you get to sublevels where you have more than 1 orbital, you put 1 electron in each box. And keep doing that until you reach the end of the boxes, and then you go back and pair them up as you need to have all the electrons you're going to put in that sublevel. Now, since what we're going to do is hybridize only 3 orbitals here, we're going to leave one of these p orbitals alone. So we're going to leave this one alone. Okay? We're going to hybridize these. Alright? So when we hybridize these then, 1s doesn't change. We're going to put those 3, we're going to make those 3 all the same kind of orbital. They're going to change their shape, their energy, everything. So they're going to be a new kind of orbital. Since they're hybridized, they're not s's or p's anymore. There's something in between. They were in the second primary level. They're s, p. How many p orbitals did I hybridize? 2 of them, so it's not sp3, it's sp2. And we're going to leave that p orbital down here alone, so we're going to label that 2p. Okay? We had 4 electrons in the valence level, so in this hybridization we're going to put 4 electrons in those 4 orbitals, one at a time, and go back and pair them up if we need to. We don't need to this time. Okay? So now, this is the p orbital that I didn't hybridize right there. See that? With oxygen, it works the same way. With oxygen we had 1s, 2s, 2p. With oxygen I need 4 electrons in the p sublevel. Okay, so there's the orbital notation for oxygen before I hybridize anything. I'm going to hybridize these 3 orbitals and leave this one alone. Okay, same thing. Leaving this one alone on the end and hybridize those 3, and so we get this, or something like this anyway. It's 2sp2, hybridizing 3 of the orbitals and leaving the 2p alone. We got 6 electrons here. So put 1 in each of the boxes and came back and put more in there as I need it. So I'll have 2 orbitals with 2 electrons in them. That's all you can get in an orbital, right? You can't get more than 2 orbitals, 2 electrons in an orbital, because you can only have 1 upspin and 1 downspin. You have to cancel out the spin, cancels out the electromagnetic repulsion that would make those electrons typically fly apart. Okay, so now this 2p is what I have here. All right, that makes sense? The p orbitals are going to share their electrons by sharing their orbitals side to side. Now, when we're doing hybridization previously, we said that hybridized orbitals form a single balloon shape. The s orbitals, which were spherical, become a single balloon shape. The p orbitals that are hybridized become a single balloon shape instead of a double balloon shape. So we're going to have an orbital like this on the carbon and like this on the oxygen toward each other. We'll color code this one green. So our p orbital's blue, this is green, and they're going to reach out to each other like this. Reach out like this. Maybe I should use the black marker to see what's going on. Okay? And that's how you're going to combine those orbitals into a bond, and combine these orbitals here into a bond. All right? So then we can say that maybe this one here is our green one. Well, that leaves me 2 more hybrid orbitals I have to make on both of these. There's 2 more hybrid orbitals. So those need to be as far apart from everything else as I can get them. So one of these is going to be swinging out toward you, and one back behind. And over here the same. One kind of swinging out toward you, and one kind of swinging out behind everything. We'll make the ones in the front orange. And let's see, let's make this one orange here. That's the one I've hybridized there. And we'll make the ones in the back purple. And we'll call this one purple. Okay? Alright, that's what's going to happen. Now remember, these are sp2 hybrids. The purple and orange are sp2 hybrids. The green ones are sp2 hybrids. The p orbitals are unhybridized. When they actually form the molecule, the carbon to oxygen bond then, when you overlap 2 orbitals that are going on the line between the 2 nuclei, the atoms, they reshape a little bit into that hot dog shape. So there's our green shared set of orbitals then when they actually share. Okay? The 2 oxygen orbitals over here, they're full. They have 2 electrons. I can't put any more electrons in this orbital here or this orbital here, which means these 2 are full. So they're going to stay in that single balloon shape. The double balloons, which are the p orbitals, they're reaching out across to each other. Okay, so they're making a single pi bond by doing that. So these p orbitals up here become a pi, which is, you know, the symbol pi, bond. Two nodes of the same bond. This is the same bond. Both parts of these are the same bond. Now, the two carbon orbitals here and here, the purple and orange ones, they only have one electron in them. So they're going to be able to share electrons with this hydrogen we have up here. Okay, two hydrogens. So what's going to actually happen is we're going to have hydrogens out here that are going to overlap or combine orbitals into a bond. And so this one will make orange, and this one will make purple. And so we're going to form that Wiener sort of shaped bond because we're overlapping orbitals in a line between the two atoms, and hydrogen becomes a sphere. So this one we're going to make, I'm just going to color code it as orange. And we'll color code this one as being purple back here. And so this is actually showing us the shape of the bonds. Now remember, when you make your actual balloon molecules, the carbon and oxygen don't show up. All we see is the knot that ties everything together there. Does that make sense? Alright, so that's what we're working on. That's what we're going to be doing today, is make a molecule. Remember, to make your hydrogen, you've got to start off with a balloon like this. We've done this several times now. You should be experts at that stuff. And then you blow up a long one that's the length of, from your little fingertip to your thumb tip. That's the length of your sigma bond. When you overlap a bond directly on the line between two nuclei, that's called a sigma bond. So between the carbon and the oxygen, you're going to have this bond in the middle. Okay, so this is going to go between the carbon and the oxygen. But in order to make this work, you've got to tie off a little piece on the end first. Okay, you've got to do this tie knot right here, so you've got something to tie with. Okay, to go between the carbon and the oxygen. And then you make your balloon like this, so you've got something to tie on both ends. If you don't do this first, you're not going to be able to make your model work out. Alright? Then your double bond has to also start with a little piece tied off like this. Okay, got a little piece on the end you can tie with. And you're going to make it 1.5 times the length of your bond that goes between the two atoms. So this is going between oxygen and carbon directly on that line, so that's the sigma bond. The pi bond has to stretch around it. So I need to make the pi bond a little bit longer so that they can stretch from here to here. See how that works? And then it stretches across the top the same way. I don't know if I think this will work like that or not. I'll stretch like that. Well, what it comes out to be is this. Okay? So that's this is your sigma bond right here. Okay? And your pi bond goes above and below. Alright? Now then, so you're going to have on the oxygen two hybridized lone pairs. Okay, they're sticking out here, unhybridized or hybridized orbitals. If there's nothing bonded to them, we make with round balloons, what we call party balloons. We'll just switch that off over right there. Okay? And so you're going to have, oxygen has two lone pairs. They're hybrid orbitals, so we're going to make those as single round balloons here, two of them. All right? And on the carbon end, over on the other end over here, we've got two hydrogens bonded to that. So they're going to look like we've been making them before, and basically you get this thing. Okay? So oxygen is right here, right in here between the balloons. Okay? And we've got two lone pairs. They're hybrid orbitals, so they become single balloons. This side of the single bond here is also a hybrid orbital. That's an sp2. So this and this and this right here are hybrid orbitals. The unhybridized p orbital makes this yellow balloon. You've got one part of the p coming up, one part going down, and then reach out to grab the one of the carbon over here. And the carbon has two single bonds, one single bond going out here, called a single bond if it's on a line directly between the two nuclei. Between the nucleus of the carbon and the nucleus of the hydrogen, straight line, that's a single bond. So you've got an sp2 hybrid here, an sp2 hybrid right here, an sp2 hybrid right there. These are sigma bonds. Okay, so this is a sigma bond in the middle, but across the top and bottom, that's a pi bond. Okay, it's all the same pi bond because they came from the same p orbital. Remember, the p orbital had double nodes, right? Two balloons. So it's a single pi p and a single p over here. When they join together, make a single pi bond. So that's the model you're making today. You got it?
Yeah.
All that makes sense? A lot of theory to throw at you, but that's why I'm making the models so you can see how it comes together. All right? You